Okay, now let's jump back into another concept we need to think about. It's about bodies in contact with one another. So if we have two bodies that are in contact with one another without slipping, and the the points in contact are moving along different paths, well, we can learn something. What we learn is just the tangential component's acceleration will be the same. So what that means is the angular acceleration of b times the radius of b will be equal to the angular acceleration of c times the radius of c. The normal components of acceleration, though, will not be the same. Another common type of problem in counter dynamics is rolling motion without slip. And we can analyze this using our relative velocity and acceleration equations. We've already learned that when we hit rolling without slip, the velocity at the bottom is 0. What about the acceleration? So in this case, point G moves along a straight line. If you know the angular velocity and acceleration, then the relative velocity and acceleration can be applied to point A. At the instant A is in contact with the ground, the point A is in the instantaneous center of zero velocity. However, this is not a point of zero acceleration. Just because it's an instantaneous center of zero velocity does not mean it has zero acceleration, because that point is accelerating that direction. Has no velocity yet, but it is about to accelerate. Or it is accelerating, and so the velocity is going to change as it lifts off the ground. So, since no slip occurs, the velocity at A is equal to 0. And we can look at the velocity of G knowing the angular velocity. Now, since G moves along a straight line path, the acceleration at point G is horizontal. Just before A touches the ground, its velocity is directed downward, and just after contact, its velocity is directed upward. Thus, the acceleration at point A accelerates upward as it leaves the ground. So if we plug all of this in, what we get then is the acceleration at point G is going to be simply equal to the angular acceleration times the radius. And the acceleration at point A is going to be equal to omega squared r, which if you look at it, this is our tangential component and this is our normal component of acceleration normally. That's how we write them. So you can see that both are experiencing two very, very different types of acceleration. Okay, that's the big thing I wanted to show you here. It's just two cases. One we have gears connecting and one we have a thing rolling around. And so now we're actually going to jump into an example. So thank you for listening. I'll see you all next time. Have a wonderful day.